Hey everyone, welcome back to the AI with Arun show. I want you to close your eyes and imagine standing on a windy beach in Boca Chica, Texas. It is May 22, 2026. In the distance, a steel monolith stands. It is taller than the Great Pyramid of Giza. Suddenly, a roar louder than 1,000 thunderstorms shakes the sky. This isn't just another rocket launch. This is the birth of a new era. On May 22nd, SpaceX launched Starship Flight 12, or IFT-12. And it marked the historic debut of their highly anticipated version 3 hardware. But this wasn't just a physical breakthrough. It was a triumph of intelligent, automated computer brains operating at the edge of space. Today we are diving deep into the hardware, the physics, and the mind-blowing technology that made this flight a game-changer for humanity's multiplanetary future. Let's get into it. Before we talk about the incredible flight, we have to look at the machine itself. Think of Starship version 1 and version 2 as early prototypes, the rough drafts of a masterpiece. Version 3, debuting on this flight, is the finished product designed for mass manufacturing. SpaceX's ultimate goal isn't just to build a rocket, it's to build a fleet of commercial spaceliners that can fly, land, refuel, and fly again within hours. To do that, Elon Musk and his team had to completely rethink the ship's architecture, shaving off every unnecessary gram of weight and reorganizing the vehicle's internals. Let's look at how they turned S39 and Booster 19 into the tallest, most powerful flying object in human history. Look at this absolute beast on your screen. When S39 was stacked on top of Booster 19, the entire vehicle reached a towering 124 meters, which is over 400 feet tall. For context, that is taller than the Saturn V rocket that took us to the moon. To make this massive structure lighter and stronger, SpaceX used a brand new, proprietary lightweight steel alloy. It's like switching from a heavy cast iron skillet to a high-tech carbon steel pan. It can handle extreme heat and pressure without bending under the load. And for the first time, this mega rocket launched from Orbital Launch Pad 2. Think of Pad 2 as a futuristic charging dock. It features massive steel shields and a pressurized water deluge system that literally absorbs the destructive acoustic energy of the launch so the pad doesn't shatter itself to pieces. Now let's talk about the beating heart of Starship, the Raptor 3 engine. If you've ever looked at a rocket engine, they usually look like a chaotic mess of pipes, wires, and sensors. But Raptor 3 is a work of art. SpaceX managed to route almost all the plumbing and wiring internally using advanced 3D printing. This means they eliminated the delicate external tubes that are prone to catching fire or leaking. Even better, they slashed the weight of each engine down to just 1,525 kilograms, saving a massive 1 metric ton of dead weight per engine. Multiply that across the booster's 33 engines, and you've instantly saved 33 metric tons of dry mass. Yet, despite being lighter and cleaner, these engines are stronger, pushing out an mind-boggling 250 metric tons of thrust. It is pure engineering wizardry. But space is hard, and things rarely go perfectly. During the Ascent phase of Flight 12, the vehicle faced a double crisis. First, Booster 19 lost one of its outer Raptor engines early in the burn. Then, just as the upper stage S39 was heading toward orbit, one of its vacuum engines cut off prematurely. Let me explain in simple terms. The standard Raptor engine is the heavy lifter designed to work close to Earth, inside our thick atmosphere. It is designed to fight against the heavy air resistance, atmospheric pressure, of Earth. The vacuum engine is a modified Raptor engine, designed to operate exclusively in the empty void of space, where there is absolutely no air. Normally, losing two main engines during a launch means catastrophic failure. The rocket loses speed, falls back into the atmosphere, and blows up. But not this time. Thanks to the ship's robust fault tolerance, S39 didn't panic. The onboard computer dynamically realized, hey, I'm losing thrust on this side. It instantly recalculated the fuel flow and extended the burn time of the remaining healthy engines to compensate. It's the equivalent of a multi-engine plane losing a wing engine, and the autopilot seamlessly adjusting the remaining thrusters so the passengers don't feel a thing. This brings us to the secret weapon of Flight 12, its real-time mission autonomy. This isn't just a pre-programmed path, it's a dynamic computer brain. When the vacuum engine failed, the onboard computer didn't wait for human controllers in Texas to send a patch. That would take too long. Instead, the autonomous guidance system calculated millions of physics equations and thrust vectors in milliseconds. It evaluated the remaining propellant, recalculated the optimal path through the upper atmosphere, and adjusted S39's attitude. It is essentially a hyper-advanced autopilot running real-time pathfinding algorithms, much like how Google Maps instantly reroutes you when you miss a turn. This exact system is what saved the spacecraft from a premature plunge, ensuring S39 safely cut its engines exactly where it needed to. Once S39 coasted into space, it was time to test its cargo capabilities. The V3 features a newly redesigned peeler door payload bay. Picture a giant Pez dispenser, but for satellites. During this flight, S39 successfully opened this door in the vacuum of space and deployed 22 Mach Starlink simulators to test how the structure reacts to heavy separation forces. But the coolest part? S39 ejected 2 tiny companion photography satellites. These mini selfie cameras maneuvered themselves away from Starship to capture high-definition close-up photos of S39's heat shield tiles. For the first time, engineers on Earth could see the physical health of the ship's exterior in real time, right before it began its terrifying plunge back home. And that plunge back home was spectacular. As Starship slams back into Earth's atmosphere, it faces temperatures hotter than the surface of the sun. In previous flights, we watched the hot plasma literally burn through the metal joints and flap hinges. But as Spaceflight Now reported, this time S39 endured the fiery heat of reentry in incredibly good shape, showing almost none of the scary structural damage we saw in earlier flights. Why? Because the V3 features redesigned thermal tiles and a secondary insulating barrier underneath. It's like wearing a high-tech oven mitt over an already heat-resistant glove. The heat simply couldn't find a weak spot to break through. Let's walk through the final minutes of S39's journey over the Indian Ocean. First, S39 hit the top of the atmosphere at a blistering Mach 25, that is, 25 times the speed of sound. The plasma glowed a brilliant purple, but the tiles held. Second, as the air grew thicker, S39's forward and aft flaps began to dance, performing precise aerodynamic maneuvers to slow the ship down and test the limits of the new V3 frame. Third, just seconds before hitting the water, the ship fired 2 of its inner Raptor engines to flip itself upright. And finally, in a breathtaking finale, it hovered perfectly over the water before gently splashing down. Although the ship broke apart shortly after splashdown as expected, the primary mission was a flawless, roaring success. Let's look at the numbers side by side, because they paint a striking picture of rapid evolution. Starship V2 was already a giant, standing at 121 meters, but V3 stretches that to 124 meters. This might seem small, but that extra height translates to massive volume inside the tanks, allowing Starship to carry tons of extra liquid oxygen and methane propellant. Total thrust jumped from 16.7 million pounds to a whopping 18 million pounds. That is the power of those lightweight, highly integrated Raptor 3 engines. And look at the engine's simplicity. Instead of the complex, fragile external lines of the V2, V3 uses fully integrated conduits. This makes the engines exponentially more reliable and significantly easier to maintain, paving the way for rapid same-day reuse. If you ever doubt human progress, just look at this chart on your screen. This graph tracks SpaceX's payload insertion efficiency and success indices from the very first test flight, IFT-1, to May 22nd's IFT-12. Remember, IFT-1 didn't even make it past staging before exploding. IFT-4 was a victory, just because the ship barely survived re-entry with its flaps burning off. But look at where we are now with the debut of V3. The curve is incredibly steep. We went from basic flight tests to complex orbital simulations, cargo door operations, and flawless controlled splashdowns in just a matter of years. This rapid, hardware-rich testing style is exactly why SpaceX is leaving traditional aerospace competitors in the dust. So why does all of this matter? Why do we spend billions of dollars and millions of hours building these giant steel tubes? I want to leave you with one final story. Decades ago, our grandparents watched human beings walk on the moon. It was a beautiful, brief moment that seemed to promise a future among the stars. But then, we stopped. Space became too expensive, too dangerous, and too slow. Flight 12 changes all of that. By proving that a massive, fully reusable, AI-managed rocket can fly, survive, and adapt, we are clearing the path for orbital propellant transfer, the literal gas stations in space that NASA needs to land astronauts back on the moon. Within our lifetimes, because of vehicles like Starship V3, a trip to Mars will transition from a sci-fi dream into a routine flight. Imagine our children looking up at the night sky, pointing at a moving light traveling between Earth and Mars, and thinking of it as nothing more than a standard commercial flight. That is the future SpaceX is building, and I, for one, cannot wait to see it. Thank you so much for watching. Please consider joining us as a member. Click on Join right below this video. What did you think of the Flight 12 launch? Let me know in the comments below, smash that subscribe button, and I'll see you in the next episode of AI with Arun. Keep looking up,